So let's look at this first problem. We want to show that y equal to x minus x to the negative first. What? I feel like there's something all over this. It's kind of terrible. Oh well. Is a solution. Yeah, it's like I don't know. Like when I was teaching in here earlier today, this area was not so gross. Is a solution to the differential equation x times y prime plus y equals 2x. And I would say most of the time, when you're asked to verify something's solution to the differential equation, you're going to look at the differential equation. And well, let's see. If I look at this differential equation, I see the function y, and I see the first derivative of y. So I need both of those pieces before I can kind of move forward. So I'm going to find, well, I've got y already, and then I'm going to find the derivative of y. So if y equals x minus x to the negative 1, then the derivative is going to be 1 minus negative 1 times x to the negative second, so 1 plus x to the negative second. And then I'm just going to substitute all of that into the appropriate places in the actual differential equation. So I'm going to plug in x minus x to the negative 1 for y. I'm going to plug in 1 plus x to the negative second for y prime. Something I would prefer my students did if I was having them do this is I don't want them to actually kind of, here's what I'll just do it. So I'm going to write x times 1 plus x to the negative 2 plus x minus x to the negative first. I'm not going to write that it's equal to 2x. I'm trying to show that it's equal to 2x. So I don't want to start off by just assuming that it is. So let's just start with the left-hand side and simplify it until it ends up actually equaling the right-hand side. So let's see. If I distribute the x, I get x plus x to the first times x to the negative second is x to the negative first plus x minus x to the negative first. Lo and behold, the x to the minus ones cancel, and we end up getting exactly what we thought we should get. So yeah, that equation, that function, y equal to x minus x to the negative first, is indeed a solution to this differential equation. Because when we took the function and its derivative and plugged it in the right places, it ended up satisfying the equation. It gave us what we wanted. Cool. Let's do a couple more. But questions about that before we do any more? All right. They got this other one here, and they got a few over here. Most of the time, this is most of the time, I don't know what I did here. I guess I loosened the cord somehow. I don't know what's going on. Sorry, that's weird. Okay. Most of the time, this is kind of the flavor that you're going to get, meaning you'll find whatever derivatives you need to and plug them all into the differential equation. A slightly different flavor is something like for what values of the constant k does y equal to e to the kt satisfy the differential equation y double prime plus y prime minus 6y equal to 0. Same idea, really. We're going to find all the necessary functions and derivatives. In this case, I need the first derivative and the second derivative. Plug those in. This time I am going to set it equal to 0, and I'm going to try and solve for whatever k needs to be to make it work. So, sorry, I'm going to have to stop moving things around over here. Apologies. I don't know what is up with this connection. It definitely feels a little dicey. Try that again. What's going on here? All right, I don't know what the issue. I guess I could try using a different connection, right? I'm not limited to just this. Says it's on. All right, let's try. Let's go over this way. Sorry about this. Usually I don't have problems like this. Let's do that for sure. We'll go VGA instead of HDMI. Change it. Okay. Great. Okay. Awesome. I'm giant. Okay. Let's see here. Share my. I want to share screen too, but I guess I'll just show that. Okay, that's fine. That works. Seems very, very different. Ugh. Oh, sorry. Sorry. I need to make a change here. 1 second. I guess it's not that terrible. It's kind of terrible. No, yeah. One moment, please. Sorry. So why don't you guys work on doing this while I fix this here? Take your first derivative, take your second derivative, plug it all in, maybe factor something out, and then try to solve for k. Where are you? Menu items that I'm looking for. There you are. Okay, now we're in business. Hopefully we won't have any more issues. There should be two solutions here. Let's see if we can find them. So my function is e to the k times t. My first derivative is e to the k times t times the derivative of k times t, which is k. And my second derivative is going to be e to the k times t times k times another k. So plugging all that in, look what we've got. We've got e to the kt times k squared plus e to the kt times k minus 6 times e to the kt equal to 0. And I should really just factor out e to the kt here. Okay, e to the kt times k squared plus k minus 6 equals 0. So I'm trying to figure out what values of k would make this equal to 0. I want to remind everybody that e to the something is never 0. It's always actually positive. So this part here, I don't even have to worry about. It's not going to give me any solutions. I'm going to worry about setting this part equal to 0. So we're really going to set k squared plus k minus 6 equal to 0. And we can either use the quadratic formula or hopefully it factors. It does factor. But it's possible that it wouldn't factor. You'd have to use the quadratic formula. K plus 3 times k minus 2 equal to 0. So our solutions here are that k equals negative 3 or k equals positive 2. Do one. Yeah, one more. Maybe two more. Definitely one more. Let's say we had the following. This one's a little bit more wonky looking, I think. I want to show that y equal to x squared plus 2x plus c divided by x is a solution to the differential equation. What do we got here? Something wild. X times y prime plus y equals x times 3x plus 4. All right, that looks kind of funky. I feel like I'm reading the wrong. Let me double check. That looks right. Okay, sure. Yeah, this seems fine. Okay. All right. Same process. Start by finding whatever you need. So let's say I have my function y and I have the derivative of y. So I need to find the derivative of y. I would probably have preferred to have written c over x as c times x to the negative 1. So let's see here. Let's see. Y, I don't need to write y again. Y prime is going to be 2x plus 2 minus c times x to the negative 2. And I'm going to throw everything in. So I will point out, sometimes these equations, you could have y's and y primes on both sides. Then you might just write it all down, or you might work with one side and then work on the other side and try to get them to a point where they're equal to each other. It kind of depends. Here, we don't. Or I guess you could rearrange the equation so all your y's and y primes were on the same side and then start doing it. Usually they're on the same side, though. Let's see. So I'm going to have x times all of this plus y equal to, I'm going to try and get it to be equal to x times 3x plus 4. I'm not just going to say it's equal to x times 3x plus 4. Plus, it's less writing if you do it this way. Because if you did that, like if you wrote this over here, then the next step you would still write the same right hand side. You would just keep writing the right hand side. It's kind of unnecessary. So let's see. Let's multiply it out. I'm going to get 2x squared plus 2x minus cx to the negative first plus x squared plus 2x plus cx to the negative first. Looks like things are going to go my way. Those cancel. And I have a 3x squared plus 4x. And you could stop there. I guess if you really needed to, you could factor out the x. I don't think you need to do that. Great, that works. So I have one more that's a little different. Yeah, bless you. I don't know if this is likely to come up, but I'm going to do one more just because. So most of the time they're like this, where you just have like, they give you y as a function and you take y, take its derivatives, throw them where they need to go. But sometimes it's not quite so cut and dry. For example, we want to show that the equation, yeah, let's pick this one, x squared plus 2xy minus x squared equal to 6. This equation is a solution to the differential equation x plus y times y prime minus x plus y equal to 0. The same kind of idea holds here, except I shouldn't say that. So technically you could definitely solve for y in that first equation and then take the derivative and plug it in where you need to plug it in. That's not the point. The point is we'd rather not do that much work, actually. It's going to be less work if we just take that original equation and differentiate it right away using implicit differentiation. So we're going to take this equation, take the solution, x squared plus 2xy minus, that should be a y squared, sorry, I think. No, sorry, I wrote the wrong thing. Maybe I said the right thing. It should have been y squared plus 2xy minus x squared equals 6. Otherwise, why would you write both those x squareds, right? That seems really silly. Sorry about that. That should have been a y squared there, not an x squared. So that should be a y squared. So we're gonna take so then if it's written that way, you really can't solve it, right? You're kind of stuck. I mean, you could if you really try, but it would be gross. You'd have to use the quadratic formula to solve for y. Okay. So let's see here. Let's take the derivative of both sides implicitly. We're going to differentiate implicitly. The derivative of y squared is 2 times y times the derivative of y. Or as I would say, the derivative of some stuff squared is 2 times my stuff to the first power times the derivative of my stuff. For 2xy, we're going to think of using the product rule here. The derivative of 2x is 2. Multiply it by leaving y alone. Switch it up. Leave the 2x alone. Multiply it by the derivative of y, which is the derivative of y. Derivative of x squared is 2x. And I wrote the wrong thing on the right side here too. Sorry about that. That should have been 6. Apologies, not a 0. But if we take the derivative of that, then it's going to be 0. Okay. Now our job is to make this equation look like that equation. Okay. So I'm going to look at my y prime things here for a second. So I'm going to think of grouping those together and factoring out a y prime, maybe even a 2y prime. If I factor out a 2y prime from those two terms, I'm left with a y and an x. And then I have I'm going to write things in a slightly different order, a minus 2x plus 2y equal to 0. The only thing I have to do now to get this equation to look like that equation is divide both sides by 2, which is totally valid. So divide by 2 and get y prime times y plus x minus x plus y equals 0. Check. That shows that this solution is indeed a solution to this differential equation, because when we took the derivative, we ended up getting back to the differential equation. It's kind of weird, but it works. So that's the general gist for showing something is a solution to a given differential equation. So you find whatever derivatives you need and plug them in where you need to plug them in. Or occasionally, if it's something funky like this, you use implicit differentiation, and then you kind of work towards whatever differential equation you started with. Yeah. All right, let's look at the shorter looking question on the board, and then we'll look at that longer looking question with words. And someday I'll find out, I'll get that board erased so that it's not so terrible to write on. So let's look at the fun. So find the equilibria of y prime equal to a times e to the y times cosine of y, given a domain of y being between 0 and pi. Sure, y between 0 and pi. Yeah. And we're also told that a cannot be 0, which makes sense because otherwise if a was 0, then there'd just be 0 all the time. Okay. So to find the equilibria of a differential equation, what should we do? Write down what you think we should do. Like there should be, we should be setting something equal to something. I think you should write down what you think you should be writing down. Or at least think about what you think.
The same topic of equilibrium. So you can just kind of like explain what we're
Totally, yes. So when we're talking about equilibria, so literally we're trying to be in equilibrium, meaning we want to be not changing. We're trying to be solid set. We're not moving left. We're not moving right. We're kind of balanced. I often kind of think of it as like being at the bottom of a parabola. Like if you're thinking about like physically, like if gravity is working, like you're at the bottom of a valley, you're kind of stuck there. You're in equilibrium. You're not being you're not wanting to go, if you're like a ball rolling, you're not trying to roll uphill either way. That would be a stable equilibrium, actually, right? Because you're not going. Whereas if you're at the top of a parabola, balanced precariously, and you're a ball, you are technically in equilibrium because you're not moving one way or the other. But if you move just a little bit either way, you're gonna roll down the hill. You'd still be in equilibrium up there, not changing, but you'd be unstable because a tiny little change is going to push you far off away from your equilibrium. But back to what an equilibrium is, it's a place where things are not changing. In other words, an equilibrium of a function y of t equal to something is a place, is a value of y where y of t isn't changing. I know it's a lot of words to say what I'm trying to get to. In other words, we're trying to find where y prime is equal to 0. Right? If we're trying to find where something isn't changing, we're trying to find where its derivative is equal to 0 because the derivative is exactly the rate of change. So that's always how we find equilibria and for sort of differential equation. You set your derivative equal to 0 and then you solve for y or whatever your function is, usually y. But I will point out, we're not trying to solve for the input, right? So technically, this equation here, y prime equals a e to the y cosine of y, where a is a constant. That equation, well, I would say that's an example of a differential equation that is autonomous. Right? We are missing the independent variable. There is no time variable there. But what I really want to point out is when you're looking for an equilibrium, you're looking for where the value of the function itself. We don't care what time is. We're just looking for a place where it doesn't matter what the time is. You're looking for where y is stable, where y is in equilibrium. So we're going to set this equal to 0. And we'll do some more examples of this in a minute here because this example is not my favorite, although it's worth looking at. So you're just going to set a e to the y times cosine of y equal to 0. We know a isn't 0 because it's given, or we're asked to assume it. We know that e to the y isn't ever equal to 0 because we already said e to the y is always positive, no matter what your exponent is. So the only thing that we have to consider being equal to 0 is the cosine function. So cosine of y is equal to 0 at places what I like to think of as the top and bottom of the unit circle. So at an angle of pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, right? Odd multiples of pi over 2, except we're limited to being between 0 and pi. So really the only answer here is going to be y equal to pi over 2. That's our only equilibrium. Is it stable? I know this isn't asked that question, but we should always ask that question. Is it a stable equilibrium? Good question. So let's actually talk about the second way of finding out whether equilibrium is stable or unstable. I forget what it's actually called. I call it like the analytical method or the not graphical method. So here's what we're going to do. We're going to think of this function, what y prime is equal to. We're going to call that g of y is the typical name. So whatever y prime is equal to, we're going to think of this as just some new function of y. So we're going to say, great, g of y is equal to a times e to the, I've already seen a problem with my question here, but we'll deal with it. It'll be fine, don't worry. The problem is that a could be positive or negative, and that's going to matter. Don't worry, we'll figure it out. So now we're going to take the derivative of this. And I really don't want you to, I hesitate to even say it, but we're not taking a second derivative. Because this y prime really means dy dt. Right? You took the derivative of y with respect to the variable t or whatever, or x or whatever we're using. Whereas here, you're saying this is a function of y and you're taking its derivative. So just, it's not right to think of it as a second derivative. Not a big deal, but just one. So let's see, the derivative a e to the y times cosine of y. I'm going to have to use the product rule. So I'm going to think of it as a e to the y times cosine of y. The derivative of a e to the y is a e to the y. Cosine of y hangs out. Plus, switch it up. Leave the a e to the y alone. Derivative of cosine of y is negative sine of y. And now we're going to plug in our equilibrium, because that's how you determine whether the equilibrium is stable, or not. So now plug, and yeah, in fact, I could factor out, I guess. This is a e to the y times cosine of y minus sine of y. So let's see here. If we plug in pi over 2, we're going to get a times e to the pi over 2 times cosine of pi over 2, which is 0, minus sine of pi over 2, which is 1. So this is equal to negative a e to the pi over 2. Which, depending on what a is, could be positive or negative. So let's actually go back and let's look at the graphical method for a second. And this is not going to be so terrible, I promise. So we'll come back to this. It's not going away. So let's assume for a second that a is positive. And I'm going to graph y prime equal to a e to the y cosine of y from 0 to pi over 2. Really, I'm not, here's what I'm really doing. I'm not even paying attention to the e to the y part. The only part that actually matters to me is that when y is pi over 2, this graph is going to cross the horizontal axis. So here's what we're getting. So when I plug in 0, I get a e to the 0 times cosine of 0, which is a times 1 times 1. When I plug in pi over 2, I get 0. And when I plug in pi, I get a times e to the pi times cosine of pi, which is negative a times e to the pi. I don't care that it's giant. I just care that it's down here somewhere. So it looks something like this. Okay. But remember, we are graphing the derivative on the vertical axis versus the function on the horizontal axis. So what that means is that if y were between 0 and pi over 2, well, y would have to be increasing because the derivative is positive over here. So if we're over here, y is getting bigger and bigger and bigger. On the other side, if y is between pi over 2 and pi, well, then the derivative is negative, right? It's below the axis here. So y has to be decreasing. The arrows are pointing towards the equilibrium, which means it is stable. If you move away from it, you get pushed back towards it. So in this case, if a is 0, and notably g prime of pi over 2 is a negative number times a positive number, we have stability. So you can either tell that something is stable by either using the graphical method and seeing that the arrows point towards that equilibrium, or you can tell that the equilibrium is stable by taking the derivative of what y prime is equal to, plugging in your equilibrium and seeing that it's negative. Because look, to go from positive to negative, your derivative of this function here has to be a negative derivative because we are decreasing as we go through that point. On the other side of things, had A been negative, our graph would have looked like it was flipped vertically, right? If A was negative, then we'd be down here at the start, hitting pi over 2 here, and then some positive value over here at pi. And it would look something like this. And so now we see that at our equilibrium of pi over 2, well, now left of pi over 2, the derivative has a negative value, which means the function should be decreasing. So the y values should be moving leftward. If y was between pi over 2 and pi, then the derivative is positive. So the y value should be getting larger. So in this case, we're getting pushed away from our equilibrium, which means it's unstable. If you move just a little bit away from it, you're going to get pushed further away from it. It's like being at the top of your scary parabola. So here we have that g prime of pi over 2 would be positive, right? Because again, if a was negative, I know, sorry, I should write down the as a reminder. G prime of pi over 2 was equal to, I know it went away. Where'd you go? It was equal to negative a e to the pi over 2. So if a is negative, then negative a is positive. This whole thing's positive. So g prime of pi over 2 is positive. That's going to give us instability. So there's two ways of determining stability. You can either use the graphical method and see that it's stable when you go from positive to negative, unstable if you go from negative to positive. We're always going from left to right. Or you can use the other method. I know there's a name for it. I don't remember what it is. Where you take the derivative of your thing your derivative is equal to, and then determine at each equilibrium if it's positive, meaning unstable, or negative, meaning stable. Cool. We'll do more examples, but questions about that before we do another example. Let's do an example with nicer numbers. Yeah. So let's say we had something like, sure. dn dt equal to n cubed. Let me see for a second here. Sure. Sorry, I had an example all set up in my head and then it went away. That'll be fine. Square minus 3. Why am I trying to make this hard on myself? N cubed minus 5n squared plus 6n. Cool. And we're going to find and classify the equilibria. All three equilibria. So whether or not we're going to use the graphical method or the non-graphical method, we still have to find the equilibria by setting this whole thing equal to 0. So set the whole thing equal to 0. Factor out as much as possible. I can factor out an n. I'm left with n squared minus 5n plus 6. Factor further. It's going to be n minus 3 times n minus 2. So it looks like our equilibria are n equal to 0, n equal to 2, and n equal to 3. I have a good follow-up question too. So let's do this the non-graphical way just to test ourselves. So non-graphically, we're going to find, and again, it is very common to call this g of whatever your variable is. So we're going to say that g of n is equal to n cubed minus 5n squared plus 6n. Then we're going to find the derivative of that. G prime of n is going to be 3n squared minus 10n plus 6. And then we're going to plug in each of our equilibria. So g prime of 0 is going to be 0 minus 0 plus 6, which is positive, meaning it is unstable at that equilibria. We'll graph it too, because I do personally think the graphical method is better. Like it's just easier to see what's happening, but it can be harder to actually do the graph sometimes. So let's see, g prime of 2, something at 3 times 4 minus 20 plus 6, and that's just going to barely be negative. It's going to be negative 2, which is negative. That one's going to be stable. Finally, g prime of 3 is going to be 27 minus 5 times 9 is 45 plus 18. That doesn't look right. 27 minus 5 times 9 is... I plugged it into the wrong thing. That's why it doesn't look right. I was really worried I was going to get 0 there, which I definitely shouldn't be getting 0. So I just found g of 3. I should be plugging it into the other thing. Not g of 3, g prime of 3. That's going to be 3 times 3 squared, which is 27. But then 3 times 10 is 30 and 6, and that's going to be slightly positive. So unstable. Or more easily, in my opinion, graphically, I've got a cubic function. The intercepts are 0, 2, and 3. Zero, 2, and 3. And I know that it's going to be going up at the very end because it's got a positive leading coefficient. So I know it's going to look like this. And then we can see that n is increasing over here, and is decreasing between 2 and 3, and is increasing between 0 and 2, and is decreasing left of 0. So that way as well, we can see, oh yeah, 0 is unstable. So is 3, 2 is stable. All right, fun question. I have enough room? Yeah. And then we'll hit that question over there. So given an initial condition, say n of 0 equal to 5, what's the limit as t goes to infinity of n of t? Well, I can plot this point on my graph here. N of 0 equal to 5 should be plotted on the horizontal axis. I know I don't have any t's here, but all I'm really saying with this is that sometime, I don't really care what time it is, at some time n is 5. Great, I know where 5 is. 1, 2, 3, sorry, I've 0, 1, 2, 3, 4, 5, right about there. All right, so let me ask you all. If we start there, which way is n getting pushed? To the right or to the left? Tell me, say it loud. Right, to the right. Right, because the arrows are pointing to the right. Is that ever going to stop? No, right? I mean, it just keeps going to the right, to the right, to the right, which means n is getting bigger and bigger and bigger. That limits infinity. Now, what if we change it up just slightly? What if I said in this other case, n of 0 is equal to 1? Now, what's the limit as t approaches infinity of n of t? Write down the answer you think it should be. Or think of the answer if you don't want to write it down. Okay, well, there's 1 right there. If we start there, we're going to get pushed closer and closer to 2, to the equilibrium that is in our way, that's stopping us from going anywhere else. And that would be true if we started anywhere between 0 and 3. We would get pushed back towards 2. So if I had said that n of 0 was equal to 2.8, we would also have the limit being equal to positive 2 because we're getting pushed in that direction. Neat. All right, let's look at that wordy question over there. So what's that say here? Assume W of T denotes the amount of radioactive material in a substance at time T. Cool. W of T is amount of radioactive material at time T. Radioactive decay is then described by the differential equation dw dt equal to negative C times W. You don't really need the negative there, but it's fine. With W of 0 equal to, what does that say? W of 0 equal to little w? Did someone write? And someone wrote this, right? Do you know what it says? Okay, cool. So W of 0 is just equal to W. I'm going to give it a W naught because I can't help myself. And C is a positive constant. Yeah. So I will point out that the way I would phrase this is just that dw dt is equal to a negative constant times W. So basically, if you have exponential growth, yes, I'm saying exponential. I know it's going to be exponential, even though we haven't solved the differential equation yet. But when you have a rate of change being proportional to the population size. So over here on a different piece of paper, real quick. Maybe someday. We'll come back to this, I promise. So if the rate of change of your population is proportional to the population size, what that means is if you have people, they're going to make more people, right? The more people you have, the more people they're going to make, but the more animals, the more whatever, cells, etc. So if this is the case where population, the rate of change of the population is proportional to population size, that's going to be, sorry, there was a word I was looking for here. Right, that constant is going to be positive, right? Because the population is growing. Whereas in this case up here, the amount of stuff you have, the population of radioactive material, if you want to use that word, it's a dumb word to use, but fine, is decreasing, right? You have radioactive decay. And so the constant here is going to be a negative constant. But you don't actually need a negative sign to represent that. We could have just said no negative sign, and then we're like, C is going to be negative, but we can use the negative here. In either case, when we solve this, we're going to get that the solution is your usual exponential growth model or exponential decay model. So I know before even doing anything that we're going to be getting something like n equal to a e to the k times t. And that's a pretty typical thing that happens so often that you probably just want to kind of be aware that it's going to happen. Like we can totally solve this differential equation. Right? Like if I was going to solve by separating variables, I'd have 1 over n times dn equal to k times dt. I'd integrate both sides. And we get the natural log of the absolute value of n. But I talked about before how you can just kind of ignore the absolute value and everything's going to work out fine. This is where I'm going to try to pretend like I can actually do that. Meaning like I can never actually let myself pretend like it's not an absolute value, but I will do my best. So we integrated both sides. We got natural log of n on the left. We got k times t plus a constant on the right. And then we exponentiate both sides. E to the natural log of n is just n. E to the kt plus c is e to the kt times e to the c. But then e to the c is just a new constant, which I like to call a. So look, we exactly get n, or n of t, equals a e to the kt. So it is true that when your differential equation is specifically that your rate of change is proportional to your population, or your rate of change is a constant multiple of your function, that always leads to exponential growth or exponential decay. Always, 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 always. And it's kind of the most important differential equation we use in this class. So it's good to be aware that that's what happens, because later on in 17C, we're going to come back to this whole idea again. So this idea, this particular differential equation is not going away. It's going to be with us for a while. So back to the question at hand. Right. So W0 is W, C is a positive constant, and we want to figure out what W of T is. Well, great. So we're going to do the same thing we just did. So I should point out, this is an example of separation of variables, where we just bring all the W's to one side, all the T's to the other side. I'm going to do the same sort of thing. I'm going to say that 1 over W times dW, or if you prefer, you can write dW over W is equal to, sorry, it's a little bit back. There we go. Is equal to negative C times dt. And then we anti-differentiate both sides. On the left, we get the natural log of W. On the right, we get negative C times T plus some constant. I'm going to call it L, just to change it up for once. Same stuff, exponentiate both sides. You get W equal to e to the negative C times T times e to the L. And then e to the L is a new constant. I like to call it A, but I think here I should call it W naught. So I'm going to say that W is equal to W naught, or W of T is equal to W naught times e to the negative CT. And yes, if we plugged in T equal to 0, we would in fact get W of 0 equal to W naught times e to the 0, which is just W naught. So there's our solution to part A. That's your function with kind of no constants solved for, which we don't really have any other information. Oh, we have some other information here. Okay, great. So the point to get here is that if you have this differential equation where your derivative of your function is a multiple of your function, you know it's going to end up being exponential growth or exponential decay. Always safe to assume. So then, second part here, we're given that W of 0 is equal to 880 grams. And W of 5 is equal to 170 grams. They're not very nice numbers. Time is measured in places. So at 0 minutes, we have 880 grams. 5 minutes later, wow, it's really decaying fast. We have 170 grams. Find the decay constant C and determine the half-life. Cool. So whenever you have this kind of question, which really we've done all the calculus there is to do here, the rest of this is just using some algebra skills and some pre-calculus skills. I like to make a table. I find it to be very helpful, where my times are on the left and my amounts are on the right. So at time 0, I'm going to have 880. At time 5, I'm going to have 170. All right, so you can do the first step of plugging in T equal to 0 and W equal to 880 and saying that 880 is equal to W naught times e to the negative C times 0. But you can also just skip that step because e to the 0 is 1. W naught times 1 is W naught. So W naught just equals however much stuff you have times 0. People often say that, right, this amount here is your initial value. Jumping the gun a little. Okay. So we get that 880 is equal to W naught. We rewrite our model now so that we have W of T equal to 880 times e to the negative CT. And then we do the whole thing again. We plug in the other data point we have. You almost always are going to have 2 data points. Plug in the first one to find C, plug in the second one to find, well, sorry. Usually I would write this as CE to the KT. So I'm thinking, plug in the first one to find the constant out in front, plug in the second one to find the decay constant or the growth constant that's multiple, that's in your exponent. So we're going to plug in W equal to 170 and T equal to 5 and solve for C. So divide both sides by 880, you get 17 over 88 equals e to the negative 5 times C. Take the natural log of both sides. You get negative 5C. And then finally, solve for C. So C is going to equal the natural log of 17 over 88 divided by negative 5. I will point out that they said that C was a positive constant called the decay constant. And it is because natural log of 17 over 88 is a negative number. It's a natural log of a number that's less than 1. And so you're between 1 and 0 where the natural log gets super duper negative. So this is a negative over a negative, which is a positive. Finally, find the half-life. I still like to use my table here. So now we're just asking the question, how long until we get to how much? Well, half of what we started with. So half of 880. which you could multiply out, but actually it's not in your interest to multiply that out at all. Here's what I mean. Paper, come on, paper. So if we're smart about this and just leave that as is, then when I take my equation, W of t equal to 880 e to the there's something here that negative c. I really not a fan of this negative number part here. Negative natural log of 17 over 88 over negative 5. Seems real dumb to write negative 5 there. Times t. Then I'm going to plug in that for w and solve for t. But look, plugging in that for w makes it really, really easy to compute this first step here, where I divide both sides by 880. I'm going to make this a positive. Natural log of 17 over 88 over 5 times t. So now I divide both sides by 880, and not surprisingly, we get 1/2 on the left and e to the stuff on the right. And so it's very much like solving for the decay constant in the previous step. Take the natural log of both sides. The natural log of 1/2 equal to the natural log of e to a bunch of stuff is just the bunch of stuff. And then solve for t by multiplying both sides by 5 and dividing both sides by the natural log of 17 over 88. I will point out, for anyone who's ever had chemistry, you've probably seen the fact that the half-life is always going to be the natural log of 1/2 divided by your decay constant. Or it might be the negative natural log of 2, or depending on who's throwing science where, it might be the net positive natural log of 2. But it's always this idea. It's a natural log of 1/2 or 2 divided by your constant, your decay constant. So we're going to get that t is equal to 5 times the natural log of 1/2 divided by the natural log of 17 over 88. Whatever that number is, if you pull out a calculator. I will point out that this time should be positive, right? It doesn't make sense to go back in time for these kinds of problems, and it is. Actually, that's not entirely true. Sometimes it makes sense to think about going back in time if you're trying to figure out how old a tree is or something, and you're given some amount of carbon, but okay, whatever. Usually just call that back in time times 0, and then your future time is how long it took. Anyway, this is a positive number because both natural log of 1/2 and natural log of 17 over 88 are both negative numbers. All right, and we are out of time, speaking of time.